I'll start streaming there, and I have also audio, and then I can start my show. So basically, you already probably have taken a look at the OMA workspace, which is quite empty. I'm using it only as the announcements channel, which I haven't done yet, any of those, and also there's a link to course homepage, which has everything on it. Oh, I promised to turn this camera that way. There's a person coming late. Yeah, I know, I have a weird sense of humor. So course homepage has everything on it, well, except some obvious stuff. But anyways, don't expect anything on OMA, but go to the course homepage, which is actually on the Google Sites. Metropolia, as you know, is a partner with Google, meaning we have given the right hand little finger. The left hand little finger is for Microsoft, and this is for Google. So, okay, no little fingers anymore. And there's everything. Oh boy. There's everything what you need to know on the course is right on these pages, which unfortunately are still a little bit under construction. So I have actually gone through up to the signals, which is today's exercise. The material is checked until that one. I still need to go the rest of one, but don't worry, I have plenty of time now. And then the enrollment, you just use OMA services to enroll. Is there anyone who did not enroll yourself before this morning? Everyone has enrolled. Excellent. So if you're not, well, just do it now. Okay, and table of contents is there. So basically, we go all of these things together. So today is about the general stuff. And we go to the signals, signal fundamentals. Next week, systems fundamentals. Then system responses, and so on. The only exception is that on week, does it start 11th of September or something like that, I will be having a fishing holiday there. That's basically part of my deal. I have 3 weeks of work on August, since I also take care of the this ICT summer school, and then I have made a deal that I will have one fishing vacation at the middle of the prime time. Deals are good. Okay, but anyways, at the end, you will also have individual exercise there. Well, I will talk about that one later on. It's not a big deal. It's just about that since all of the other exercises are group exercises, then I also need to check what you are really made of. So the first 7 exercises are 10 points each. Then the last one is 30 points. Okay. We don't have any exams. Just weekly exercises. Just. Yeah, at the end of the course, you wish you had just the end exam. But anyways, so this actually is considered one of the hardest topics in the field of ICT, and you are lucky, since I think most of you are embedded systems students. You are still required to take this. This is called, in future, this is called job security. This is stuff which never goes away. It will be there forever, as long as we have binary logic. We have digital signal processing. All right, this hard topic, it requires a lot of work. But on the other hand, at least myself, I found it a little bit too much interesting topic. So basically, that's why I'm here. Okay. On the general stuff, basically, I have this stream. So basically, let's just check if it works or not. It should show me on the general stuff. Basically, I have this. Good. Did I have any audio there? I hope I did. Good. Did I have any audio there? I hope I did. Do I have audio? Good. Did I have any audio there? I hope I did. Is there anyone with a mobile phone who could actually check that audio stream is also there? I set up and tested it this morning, but you know, for some reason I couldn't get it from the browser. And basically, after the classes, I will replace this streaming link with this video clip to YouTube. All right. Then I also have these slideshows. And let me start immediately with the slideshow. Okay. Does it go? Okay, I probably should actually start it from here. All right. Yes, I have audio. Thank you. So, all the material are also in Google Slides, and they are licensed under the Creative Commons 4.0, meaning that you can use it for the you know, any non-profit educational stuff, as long as you can you actually mention my name there. Okay, that's fine. Okay, so digital signal processing, I do not have the complete picture here. It's just a brief summary. So don't expect to have everything on the slides. There are also wonderful books available on the digital signal processing. Let's see, yes, this is the correct kind of thing. So wonderful books. I myself personally, I'm old guy, so I prefer these real books printed on paper, preferably Finnish paper. And this is my favorite one. It's Sanjit K. Mitra, Digital Signal Processing, very practical engineering approach to the topic. And this is, I think, something like 4th or 5th edition already. There. Welcome. Hi. And you're also late, so I'll take you on the take you on the picture. All right. So, and then I had the another one is actually pretty good, since that's also free to use for non-profit things, dspguide.com. So a full engineering textbook on the topic, free to use for you, especially for this kind of courses. Wonderful, wonderful thing. Okay, and then there are plenty of. I have also found this digital signal processing by Sanjit K. Mitra on internet as a PDF. And it was a pirate version. Never use pirate copies, especially on the engineering textbooks. You know, engineering is a profession. It's not a hobby. I don't care what you do on your hobby time. You can do illegal stuff. You shouldn't, but you can. But when you are in a profession, never do anything which is even on the gray area. Okay, some life advice too. All right, so why I'm doing this? That's a question which you should ask yourself every time when you enter a classroom, or well, doing an engineering job or whatever. So those are some of the reasons I found basically for myself. I just started thinking why I did take the digital signal processing at the first place. Well, it's practical and useful topic, yes, especially for embedded engineering, smart systems. You need to know how to handle sampled data. You need to know how to use the sampled data to control the system. And without this stuff or information or knowledge, you will end up killing someone probably. And that can be yourself. So okay, it can actually come dead serious. There's some say the classic things like how to kill people by X-ray machine by just typing a bad kind of code. Okay, you maybe have already heard of that. That was something 60s or something like that in United States. And there have been also all kind of glitches on the digital signal processing stuff, and so be careful. Okay, because basically this is not theoretical topic. We are connecting physical and the matrix, you know. Yeah, I'm that old. I remember Matrix when it came out on the movies. All right, and mandatory course, yes. For me, it was mandatory, but I've found it very, very interesting at the beginning. Okay, and I need this because someone told me so. Interesting? Yes, it is interesting. Finally, you have some use for the math you have been learning. Okay, finally. Oh, by the way, talking about math, on your schedules there is also a introductory complex numbers classes by Timo Salin. So especially for the Finnish students who don't have anymore the you know, this complex numbers is not part of the first year studies. So basically you should take that Timo Salin's extra stuff. No, it's not extra, it's part of this course. I think it's on Friday or something like that. But check the calendar. Okay. Find out how digital systems actually work and create your own phone ringing tone or well, some other amusement kind of things. What you should know before. Fundamentals on math like functions, done. Complex numbers, either done or this Friday. Statistics, you have done some of that. Integral, not necessarily integral. What is this? Muunnos. For transformations, but you know, integral overall. Derivative, polynomials. That's it. Some special kind of things like series, Fourier transform, Z transform would be handy, but I think Timo will go through the Fourier transformation on Friday. Okay, good. So if you find something here that you need to polish up your knowledge, you know, there's plenty of things on internet. Especially there are these edX courses. There are also the MIT depository of their stuff. Very boring lectures, taking videos. So it's just like what I'm doing here, just a video of a lecture. People drawing on the blackboard. But still, you know, the best what Americans can do on the field of engineering education. Boring stuff, still. Okay, topics. Yes, we have some topics there. So digital signal systems, filters, system modification, embedded systems. One more topic is missing here. I'm also including here the fundamentals of control theory. Well, I call it systems control, since control theory is very high in math. We are going directly how to empower the that's higher mathematics to do something. Okay. Good. Enjoy. So, other stuff what I have, since we have these exercises, there have been some classical mistakes, and I kind of got enough of writing the notes over and over again why something was wrong. So please take a look at this one, frequently appearing mistakes on the exercise returns. Okay, and on the top of the list you will be actually returning the exercises as group exercises, except the last one, so that basically it's a link to a Google Doc that I can comment for good reason. I want to give you some feedback. But say way too often I get link which does not open, or it opens on a so that I can just view it, not comment. So be sure to share it the correct way. Or another one, wrong document format. So absolutely no Word documents, links to Word documents, those are totally useless for this purpose. No PDF documents, just simple Google document that I can comment. Okay, then this is also quite general. You will be actually using some semi-random numbers, SSS, but didn't figure out it's correctly how to make it. But we'll go actually through how to do it correctly later on. And then, okay, sometimes link works, but it's wrong. Ha! And the funniest link, or not, it wasn't really funny. The worst link what I have ever got was really, boys probably guess it. That's the first thing that came into mind. Yes. Yeah, that was so embarrassing. Okay, and then another one. This is classic also. Not in Metropolia, but I also have this students coming from other cultures. Okay, this is cultural thing. In some university, I started getting 3 different versions of the first exercise, and there were 40 students on the course. Okay. Yes. Then another one. This is a very Finnish problem. Decimal separator. In Finnish, it's comma, but everywhere else it's point. It's decimal point. Okay, and the rest of that you can read yourself. But those are the most common things. Good. Then about assessment. So you need to do 90% correct everything in order to get the grade 5, which is excellent. We could actually take a look at last year's stuff to see how many of the students scored and what. Just a moment. Since just like last year, also this year, I'm also running the scoreboard. Oh, that's the virtual course, sorry. let's take the one before that. Whoa! Oh, sorry. Can't see it anymore. It's basically I removed the site. Sorry, didn't remember that. But anyways, there will be a scoreboard, and 5 means that you have done everything and did your best. You still have some room for few mistakes there. Okay, so say this is very doable, but just by hard work. And then 40% is very hard to achieve. It means that you didn't do much, but well, enough. Usually students either do this or don't do. So generally this course has a distribution of the grades something like this. So say 1s and 5s. There's of course there's some people don't do it at all. That's a little bit too high. Say sometimes just life happens and you need to skip the class. And then they are usually about the same amount of number 1s, but then the highest ones are usually 4 and 5. So that's a general kind of thing. So it just needs that you need to have stamina to do all the exercises. So this is not scientific class, but this is a engineering class. Okay, good. So exercises, as I told you, 8 of them, first 7 exercises give you a maximum 10 points each, and the last one is 30 points. Right, and again, frequently appearing mistakes, and then we also have the scoreboard, and I have found this one a kind of legal way of showing up everyone who has done what and how much you scored. Okay, so first name only, no student ID numbers, just first name. If you don't see your name here, okay, you either haven't enrolled to the class or our student record system shows a wrong first name which you have not corrected yet. So those 2 options. So this list is from 9 AM or something like that. So if you enroll after that one, I'll just add the name there. Okay, and 8 exercises, total points there, and then the grade, which will be initial until you have done everything. Good. So scoreboard. Good. Any questions this far? No? Okay. Let's then go to the signals part, but I think in my problem. Okay. So now basically let's go to the today's topic, which is signal fundamentals. Yeah, so that picture actually is from the you probably know where it was. So it was on the small church next to the Finnish the National Museum. There was last winter there was this display of Christmas trees done by the elementary school students. Okay, nice place. Anyhow, let's take the slideshow. Oh, by the way, I didn't remember to tell you, I've also used the whiteboard for a good reason, but I don't see any other. Okay, I need to find some of these, since basically I found out last year that if I'm using these slides, I'm going way too fast for anyone to actually understand what we are going through. And after the first a lecture I've actually started using the whiteboard, but I think I will start using the whiteboard right now. Otherwise, you will be in trouble. Okay, so anyways, a couple of first words and then I will move to the whiteboard. So digital signal processing, that's kind of just a general idea what we are talking about. It's that recording box there. So basically there is some voice source and a microphone or a sensor to record that stuff or get the signal. Then you get a sampler that actually records the stuff, and then you can start analyzing it. So that's basically the voice recording process. So what happens on this box? So this is a little bit of, say, goes into electronic sides, because, well, as far as I know, there's battery in these systems for a reason. That's how things work. So it has some electronics. And first step for the signal, like microphone on any electronic box, like, well, for example, like this, is to have the amplifier on it. So there's always a signal amplifier, and then after that one we have usually low pass filter, and after that one sampling circuit, and after that we have the analog to digital converter, and there you have the digital signal. But all of those blocks are there somehow. It's just all the codecs, for example, code and decode circuitry, they all have those fundamental circuits there. Okay. If we had any oscilloscopes, well, that looks like an old oscilloscope. We could actually hook up this microphone signal directly to a scope and see, okay, small signal, maybe some noise on it, but anyways, way too faint for the analog to digital converter to do any conversion, meaningful conversion. So for that reason, there's the gain, amplification of the signal. Try to match the input of A to D converter, the input range, as much as possible without clipping the signal. So as big as possible, and to match the A to D conversion the range. Otherwise you are just missing some bits. Okay, this the next block was low pass filter, so that takes care of the high frequency noise. For obvious reason, it's about aliasing of the signals. I think I have a good example of aliasing later on. Okay, what sampling and hold circuit actually do? Well, it stops the signal. So after that you still can have any voltage value on the signal available, so it still continues in the voltage or the value axis. So it's continuous signal, but now we basically have sampled time. Okay, and the next one would be this A to D converter or A to D conversion, which basically has the quantized steps of values what it can present. So basically a good A to D converter makes a rounding of those values, continuous values in the certain digital levels. There. Okay, now we can talk about sampled signal, or actually digitized signal, not just sampled. So sampling is done already on sample hold, and then it's digital after the A to D conversion. Okay, so analog signal there, meaning continuous time, continuous value. Then we have sampled signal, and at the end, digital signal. Okay, the analog signal is more about electronics, analog electronics kind of thing. We are not taking too much that one into account. But then the sampled signal is basically what we will be doing most of the time. We also visit the digital signals in a sense that if the rounding errors start to be, say, remarkable, then we have to handle it as a quantized value signals. But that's actually a quite special topic for fixed point arithmetics in computers. The sampled signals are quite nice. Then if you have a floating point precision on your calculations, then you probably want to use the sampled signal kind of algorithms there. So discrete time, but continuous value. Double precision floating point numbers are just fine for close enough to be considered as continuous value. Okay. Oh, I have a cat. Okay. Now I need the whiteboard. I'll draw something there. So alrighty. So sampled signals. So basically we have even a theorem on the sampling, Shannon sampling theorem. But anyways, the what is all about basically just any continuous time signal. So this is our f of x or f of t. Let's make it continuous time. And then we have a sampling rate. Basically, this is the unit here is the 1 over second, not hertz, but 1 over second, samples per second, or SPS. And that just tells how many samples with a constant sampling time in between are in 1 second. And basically, let's put this one here, TS is a sampling time, or sample time, which is simply 1 over fs. So basically sampling is just that we'll take a one sample on each of these points where the distance is just ts. Easy. Okay, so that was continuous time, and then actually for sample time we don't have anymore the continuous time the scale here, but more like indexing n. Index of the value, sampled value. And well, in this case samples would be something like that. There, and so on. Simple example, if this f of t was a sinusoid, for example, so x of t equals sine 2 pi signal frequency times t, then basically the same thing sampled x of n is simply sine of 2 pi. We still have this one here, the frequency times the t is here actually, or for sampling it's n, time TS. See. Yes. At that point we have 1 times TS. Here we have 2 times TS. And so on, n times TS. Simple. So instead of the t, you just evaluate that function at those time steps, and that's sampled signal. Okay. Whoops. Shannon's theorem means that you need to take at least 2 samples for a single period in order to find in order to sample the signal correctly, and that's an example what happens. So there's a blue one is the continuous time signal, and then we have the red one is the sampled signal, where we have selected the sampling frequency or sampling rate totally on wrong kind of value. So it means that it still looks sinusoid, but it's a little bit different frequency as the original one. So that's called aliasing. So you can sample only signals with frequency lower than fs/2. Okay. So f must be smaller than fs/2. Fs/2 is sometimes referred as Nyquist frequency, Fn. V, no U. Literature usually puts Nyquist here with the U. It's with V. Okay. Good. Okay, that was the digital signal, which we are going to visit briefly on the was it 7th lecture or something like that, on the very last ones, anyways. The so we are talking about the last part here, quantized value. This one here. Okay, that actually brings us some more math, and math I really hated when I was in university. It's statistics. Okay, since basically it's very random error in between of the bits. So least significant bit, think of this one for example, and we have digitized it with very rough levels. So basically anything in between of this one, or actually anything in between of that, those values, real values, will be rounded to the nearest bit. Okay, so there's a plenty of error, and it's also kind of nasty kind of looking error. It's the kind of what is that called? Uniformly distributed noise. It's not Gaussian, which would be kind of easy, but it's uniformly distributed noise around the around that real bit. Okay, so that actually brings us the quantization error, and there the quantization error also brings us to the term signal to quantization noise ratio, SQNR. Okay, which basically tells you something about how big or how many bits you should have on your A to D converter if your the dynamic range, what you are reaching is something, and the noise floor of your sensor is something. So no need to add bits if you are adding noisy bits. So that also tells you, okay, so if you have a audio signal say normal for normal audio signal is something like 80 dB range. So that one tells you it's supposed to be at least 16 bits or something like that. Yeah, 16. Yes, something like that. Yes, so it's basically you get about 100 dB. So 16 bits is also the high quality CD, but you still can hear some noise, the quantization noise. That's the flat noise level when you turn the power to the let's see, southeast and there's nothing on the record. You still hear the quantization, then you can hear the quantization noise. Okay, and then it starts and you break your ears. Okay, but anyways, so 16 bits. Why we have 16-bit A to D conversion on most of the audio data on CD? Well, that's the physiological reason for it. But well, nowadays the high quality is 24 bits, right? So that was yesterday, but now 24 is enough. And there are physiological reasons why you don't need, you really don't need more. Okay. Yeah, so that's also the why we have the sampling rate. The CD quality has 44.1 kilohertz sampling rate. If you sample it as PCM, meaning pulse code modulation, meaning just plain sampling of the values and showing those at the all the bits of it, 16. Okay. So 44.1 actually fits quite well, since you needed at least 2 samples for each cycle, so there you can actually sample 20 kilohertz signals without any problem. Okay, and then there's even that small margin for, let me draw a picture just to get you kind of in the right mood. So this is the dynamic range in dB. Here you break your ears, 120. That's 80. That's 0 dB. So fundamentally your hearing area somewhere there. That's then the 20 hertz and then 20 kilohertz, 202 kilohertz. Okay, your hearing goes something like that. You would like to hear on about that area. Okay, here you start to have some pain on this area, and here you get the permanent loss of hearing in more than 120 dB. Powers, acoustic powers. But anyways, so basically, if I just draw something else here. So usually when you are hooking up the microphone doesn't really give you any information about the DC, which is good, since basically we have this. You can have a low pass filter. Okay, let me put that one, the filter properties, or the system amplitude response, your sampling electronics amplitude response. Basically you want that electronics to be flat here, so D0 dB, and then basically it can have a high-pass filter, simple high-pass filter in the beginning, and also you can start cutting off the higher frequencies after 20 kilohertz, which is good since your Nyquist frequency is somewhere here, and you want to basically attenuate this part of the signal out. These microphones, small ones, they're usually ceramic microphones, and they are also really good for ultrasonic sounds, or they are also really good on picking up all kind of noise from the electronics. For example, well, computer, this display, they have this high frequency DC-DC converters to lift up their signals. So basically you need to get rid of also all the interference, electromagnetic interference in higher frequencies. Okay, so well, 44.1 kilohertz sampling rate would give you, say, reasonable area that you can do with high precision and with low noise. Okay, nice. Now you know. Couple of basic things about the signals. Well, that was a random arbitrary signal on the whiteboard. There are also a couple of fundamental signals that you need to know in order to actually start playing with, say, test signals, like discrete Dirac delta function. So it's basically partly integrated Dirac's delta. But anyways, it's easier to remember that, okay, so its value is 0 elsewhere except if the index is 0, then it gets the only place, only the value 1. Otherwise 0. Okay, just basically it gives 1 unit of energy at certain time, just like the continuous time Dirac's delta function gives you 1 unit of energy at certain time. Okay. Another one. I'm actually showing the unit impulse. Just for example, this point here can be expressed with the value of the signal on that point times Dirac delta at that point. And mathematically, actually, it makes a lot of sense. And the digital signal processing is based on applied mathematics. So the fundamentals why sampled signals actually are acting certain way, they come from that kind of fundamental stuff. But I'm not going to teach you more about the theory stuff. You can read the books. A unit step. All right, now we have something tangible that we could use also in real life. We have the Heaviside unit step function, which is a same as the continuous time, but basically it's just sampled. This is a good for testing systems. So you can run a Heaviside signal through a system, and it should behave about the same as in analog electronics you would use the square wave, except in square wave you need to do some fancy mathematics actually to match it with the Laplace transform, and and that gets ugly. Here we have a little bit easier mathematics, but still a test vector to any system. Or how to start a signal mathematically. Well, for example, I draw only this part, but if it's a continuous time, then it actually means that it never stops. It started before the universe was done, emerged, and it will be going after universe has already been vanished. Okay, so for that reason we actually need to limit the time, and that's the way you limit it. So you can start the signal here by multiplicating with the mu n, and you can also end your signal, for example here, by multiplicating actually, or doing minus mu n minus some capital N. So basically that's how you turn it off. Okay. So that was the unit impulse and unit step. Actually, the unit impulse is also the test vector for digital systems, since the unit, the impulse response function more or less defines how the system behaves. So basically you just take the unit impulse, run it through a system, then it gives you the unit the impulse response, and that's everything what you need to do if the system was linear time invariant system. Yes?
Yeah, my brother is actually an audio engineer, and they're using like Dirac delta kind of function.
Yes.
If you want to get the response of the system, for example, you want to record how the room sounds, or you got really someplace like a hall, big hall somewhere, and you want to make your music to sound like it was played in that hall, so you want to have nice echo in your sound. You can just put those microphones around the place and make a snap with the finger, and that is like making the delta function.
Yes.
In that case, and then you get the response from the whole hall, and you can just write it down and use it in your music, and you're making gold in all your plays.
We could actually demonstrate it.
Yeah.
Let's try this course. Yes, excellent, thank you. That's easy. That's way too easy not to demonstrate, you know. That's cool, actually. Yeah. Remind me of that one when we are going to next week on the system response. The following week, system responses. All right. So if you want to get everything sounding as boring as in this lecture, you just, you know, do it like that. Good. So yeah, more about the fundamentals of signals. So then actually we have periodic signals. Okay, mathematically it's like that. So we have a periodic signal if and only if we can find a constant time shift that you can add that constant time shift to the signal, you get the same signal without the shift. For example, sinusoids or any, say, the Fourier series are actually continuous, or the periodic signals. Okay. And the shortest time period is called base period. However, when we are doing sampling, we have to find a index, which is a integer number, to do the same thing with this sampled. And then actually what happens is something like that. Down on that picture, first of all, it's not necessarily the same base period anymore. You don't get the samples exactly on the same spots and as you wish, which means that for digitized signals it's quite seldom that you find any really periodic signals. It's more like abnorm than norm. So sinusoids do not appear as exactly periodic when you do it, say, mathematically. But of course, sampled periodic signal looks like a sampled, well, a periodic signal, but you can also see something else there. For example, well, what happens if you are taking a look at the spectrum of the signal on continuous time? You will get a on sinusoid, it's just a peak, one single peak. But when you sample it, you will always get an envelope of other frequencies around it. Always. Side lobes. You get side lobes. And actually, we can actually have the funny side lobes there too. Okay. Wow. Fourier series. Great. So basically, it just tells you that you can, if you have a periodic signal in continuous time, you can break it to the different frequencies. And when you sample that, of course, the same thing happens as in continuous space. Well, you have these harmonic signals, and of course, after sampling, you will also have the side lobes of those. Good. Wow. But the formulas are beautiful, right? All right. So we had unit impulse, we had unit step, and now we are actually into the and then we have these periodic signals, and the next class of signals is random. Okay, anything else basically other than the special functions are more or less random. Like my speech is very random. So unpredictable values and how we basically handle those when we have unpredictable values by statistical means. Which means, well, normal statistic properties plus the spectral properties, and only by statistics. Okay, and some examples. Wind noise in microphone. It's quite hard to get rid of all of this small Q turbulence on mechanical structures. Or then we also have let's see, small Q turbulence mechanical structures, and I just saw Joe disrupting me on the floor, so I need to think of the over. So small Q, yeah, but and then electronics. Electronics has this kind of two different noise sources. Always there, shot noise. If you have any current flowing through a system, you will have basically quantized carriers called electronics are moving there. Okay, so you will have a noise immediately if you have any movements of current. So you cannot get rid of that. Oh yes, you can. You just turn it off. Okay, but anyways, and then another one is Johnson noise. So basically, if you have any conductor, well, of course you have. Otherwise, these electronic devices wouldn't work. As soon as you have a conductor, you also have random thermal movements of charge carriers. And basically, if you have semiconductors, oh yes, we have even more of that. So a couple of noises you just need to live with, and basically it just states that practically every single human-made device has some noise on it. Okay, and then, well, this is just to remind you, random signals, the nature is basically either Poisson's distribution, meaning that basically it's kind of event kind of thing, so that it happens or does not happen. It cannot have any negative values then. So basically that's usually Poisson's distribution. And another one which is quite nice and easier to handle is the normal distribution. Gaussian shape histogram. Okay. Let's see how many things I have still here. I have some. Okay. So I think that this takes about 15 minutes more. Then we'll have a break. Statistical analysis. So basically, if we had these random signals, this one statistical analysis would be to calculate how many values will fit on some range, and that's histogram. And the form of histogram actually shows you if this signal is, for example, the Poisson distributed or normal, the normal distributed or uniformly distributed numbers. Okay. So it's basically a probability density function form. Okay. And then we go to analysis. Correlation. Correlation is a measurement of similarity of two signals. So cross correlation formula is there. We'll go these. We'll actually check these with the MATLAB also at some point. So don't worry if it's just sounds a little bit theoretical at this point. But anyways, cross correlation measures the similarity between signals X and Y. Okay, there are some really good applications. Basically, you can measure distances using correlation, like they do in sonar. Sonar basically just that could be a sonar sound source, and you just measure the echo. Since the first, well, let's see. I need some space here. So if you record a snapping of your finger, you probably get something like that. That's the snap. Okay, and then after a while you will get an echo, smaller one but similar shape. Then of course you have plenty of other noise here, like this obnoxious the ventilator, or someone yawns, or someone on the corridor. So you have random noise here. But if you do a correlation of, well, this part of the signal with the rest of the part of the signal, you will find the highest correlation. So that function gives you the cross correlation function. It gives you the highest level where there are similarities. So you take the highest one, and that's your echolocation. So running the correlation, let's see. This time it would be self-correlation or autocorrelation because it's signal to signal. So basically the highest peak would be at the 0, which means it happened here, but the next highest correlation would be here, which is simply the same distance as in here, not in the scale. Okay, but anyways, you will get the highest correlation there, and these random signals usually do not give any high correlation peak if your test signal was different from the noise figure of the surroundings. But from this information basically just calculate how far the distance was. So that's basically the fundamental idea of a sonar, sound radar. Okay. Convolution is a little bit different. Very little different, but it has a huge meaning. So correlation is basically sigma. So sum of x of m times y of m plus n. Okay, and in convolution we have minus n minus n. Okay, the difference is then that we basically do not correlate anymore, but we convolute, meaning we take the spectral properties of the snap, for example, and run it through the signal here. It will just clean the signal so that wherever we have the similarities, we'll show the same signal, but the noise level has been going down. Okay, so that would be called matched filtering. And this is also, the convolution is the fundamental of how you do digital filters. Okay. There's a say linear filtering is based on a convolution, meaning that you basically take a, for example, this kind of filter property. So it's a bandpass filter. Okay. So that one would be our bandpass filter, h of omega. Then you actually transform that one into sampled impulse response. And now how you do this filtering, you basically convolute this the input signal how did I mark it? Convolution with star. Okay. So this is not a multiplication, it's a convolution. Okay. So you convolute the input signal with the impulse response of the system, and tada, there you have a filtered signal. And mathematically looks like that. Ugly. Right. Okay, so correlation was finding similarities. Convolution is basically filtering. Then we have the another topic that I need to remind you is about signal to noise ratio, which basically gives you the goodness of your signal. So it's simply the signal power divided by noise power in decibels. And there you have, if the signal and noise variances are known, then we actually have the basically well, the power of the signal is directly proportional to variance of the signal. Okay, so basically just have the variances there. Okay, so you will be using this one already on the first exercise, I think. Good. Wow, even spectral analysis here. Good. Basically this exercise, I think it's on the exercise 2, yes. But anyhow, the spectrum. So this far we had the signal only on time space. Well, here we have the frequency space kind of thingy. And here we also have the frequency space. So you just need to remember that if you have any signal, it has the time base presentation, but also the it appears also on the frequency space. It's just a presentation of the signal. nothing more. Just like the time space, you just have the having basically ticks or times as the horizontal scale. But still it has a value, but it's not really tangible either. So it's equally abstract as frequency space signal. This just shows, okay, it was 2.5 volts here and 3 volts there, but how you feel 2.5 or 3 volts? You need 100 volts to feel it. Okay. And you can measure it only with some devices. So basically the frequency space equally abstract thing. There you just basically show how much power we have on the signal at certain frequency ranges. Like here we have how much value we have the signal at certain time. Okay, there we have how much power of the signal at certain frequency range. Nothing more. And then there's this magic Fourier transform that does the trick. Nothing more. Just Fourier transform a time-based signal, then it shows up in the frequency space. And inverse would do the other way around. No magic required. This I already kind of sort of showed. So this is actually a example that we have a sampling rate of 1000 samples per second, and then there is that the sine wave 2 pi 50 hertz times n times ts, and ts was 1 over fs. That wn in the front of it, it's actually the window, meaning we took a sample on some certain range. We cannot transform anything from minus infinity to infinity. It takes a little bit too long time to wait the infinity to happen. Okay, so in this case, this example, we had a square-shaped window that multiplies the sampled sinusoid. Mathematically it looks like that, and that's how it practically shows up. So there are those side lobes. Okay, so signal power has the maximum peak around 50 hertz, not exactly, actually that was 49 point something, I think. Or was it 50? Oh yeah, yes, actually it is 50, yeah, sure. I was lucky. But anyways, the peak is right there where it's supposed to be, and then there are these side lobes. And the side lobes are actually coming from the window function, but more about that on third or fourth lecture. Okay, sometimes this is not enough. One single spectrum is good only if your signal is stationary, meaning very, very, very boring. But if you have a the frequencies are changing on the signal, for example on chirp signal, which is really good. Also, you might also tell what this chirp is, since your brother is working on acoustics. So you use this is an excellent test vector for any acoustic system, since it's basically the chirp that starts on some frequency and then it ends at some frequency. Basically you can just run the chirp and you immediately get from the power spectrum you get the what was the amplitude response of the system. So basically it's just you're measuring the system with individual spectrum peaks, but at the individual frequencies, but all of those frequencies are on the one single sample of test vector. Okay, and that actually means you start with some frequency. Here I started with 0 and ended up somewhere else, maybe 500 hertz. Yes, and on the right hand side, that colored picture is now the spectrogram, meaning it shows graphically how frequencies are varying by time. Time axis on the horizontal, and then frequencies axis on the vertical, and the color coding means the power of the signal. Okay, nice. So that's how chirps looks like. Wow, I even have a questions for self-study here. So this one means actually only one thing. So we will have a maybe 20 minutes break. This was a lot of things to basically start dissolving. And let's continue at, let's see, 12:40, same place. Okay. Any questions? Good. Off you go.